Hello everybody, we're back to Dysrhythmia Made Easy, and now we're going to talk about the ventricular and arrest rhythms. If you're interested in doing your worksheet, we begin on page 6. And I just want to mention that yes, we have the 6 questions that we usually look at, and because we do this recipe and we look at the P waves first, I don't want you to get the impression that the atria is the most important. You know that yes, the atria has its function and that it is important, but the bottom line is if you don't have ventricular depolarization and pumping and contracting and then pumping, you won't have a cardiac output. So really what tells you about the stability of the patient is, are there QRS complexes? Is the ventricle pumping? And I told you about that snarky little nurse and atrial rhythms versus ventricular rhythms. So yes, it's a nice shortcut that if the QRS is narrow, then you know the ventricle's okay, and therefore you can have some time to figure out what kind of dysrhythmia you have. But I don't want you to get the impression just because we're looking at the atrial, the P wave first, that the atrial is the most important. Truly, the ventricle, the pumping chamber, is the most important. Let's look at this first rhythm and determine what it could be. And again, there's your 6 questions that are before you where you can pause and try and identify what this rhythm is. We ask our first question, are there P waves upright? Well, I don't see any P waves. I just see these tall little mountains. So the answer to question 1, there's no P waves. Definitely, we do not have a rhythm first name of sinus. Is there a P? Well, we can't answer question 2 and 3 because we don't have a P wave to begin with, so there's no way that we could answer 2 and 3. When I measure the QRS, you can see where I made my line. The QRS complex begins here, the QRS ends here, and when you measure that, it measures 0.32. This is a wide complex. It is greater than 0.12. Therefore, by the Hughes-Kloof method, if you have a wide QRS complex, then the first name of my rhythm is ventricular. Let's look now at the rate. If you calculate the rate, there are 25 complexes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. We have 25 complexes times 10. We're going to call this a 6-second strip. We have a rate of 250. Very easily, we put the two together. The first name of my rhythm was ventricular. The second name of my rhythm, because it's very, very fast, is tachycardia. This is ventricular tachycardia. Now notice that this is a very regular and fairly organized looking rhythm. And we'll talk about treatments for these rhythms later on, but know that ventricular tachycardia, again, anytime there is ventricular abnormalities, this is an emergency, and you would need to take care of your patient and address this issue very quickly. Let's look. My computer is stalling. Let me just make sure I haven't skipped, and I haven't. Let's look at this next rhythm. You can see this. Again, pause your computer and try and identify what this is. Most of you probably know already what this is. When you look at the P waves, you say there aren't any P waves. Maybe those are P waves, but I don't know. There's just no organized electrical activity. All I see is a bunch of bumps, and therefore I can't answer the question to 2 and 3. I can't do anything about QRS because there isn't really a discernible or easily identifiable QRS complex. I can't calculate the rate. This, therefore, is ventricular fibrillation. In other words, I don't have a ventricular complex to see, to identify whether it's wide or narrow. I don't have any complex. All I have is some waves that are disorganized looking. And by definition, this is ventricular fib. You'll see it V-fib. Sometimes it will be, the waves will be bumpier. They will still look like this, but it'll be bumpier or bigger. But again, notice when you look at VTAC how organized and regular it is. V-fib is always irregular. It's disorganized looking. This is fine V-fib. Now let's look at this rhythm. This is a little bit more interesting. And we've got the 6 questions that we can answer to this. This is where a lot of students go, I have no idea. So let's look at it and do your recipe and take each piece at a time. So when I ask you the question, are the P waves upright, you might be able to notice that there's a pattern with this rhythm. I have normal complex, P, Q, R, S, T, and then this funky looking thing, and then I've got a P, Q, R, S, funky, P, Q, R, S, funky looking beat, and then P, Q, R, S, and another funky looking beat. So let's look at the normal beats. And when I ask the question P waves upright, I can see that in our normal looking complexes, the PQRS complexes, I can see that there are those beats and they have normal upright P waves. So we're going to focus on these normal beats, this beat, this beat, this beat, this beat, these normal looking beats. Those came from the SA node. So is there a P wave before each of these normal looking beats? Well, yes, there is. When I look at the PR interval of the normal looking beats from here to here, it measures 0.16. Well, that's normal. And then when I look at the QRS of these normal looking beats, it measures somewhere between 0.04 and 0.06. Well, that's normal. And if you count all of the beats, it's a rate of 80, and then you've got these 4 beats that are normal. Well, what's a rhythm? Well, I can say that, well, these are sinus beats, but I can't call this normal sinus rhythm because I've got these funky beats. So let's look at the funny looking beats or funky looking beats, however you want to do them. You'll have some people abbreviate them, FLBs. And let's talk about the P wave. Is there a P wave before these funny looking beats? Well, no, there isn't. This is the T wave from the PQRST. So there is nothing before these beats. I see what looks like a QRS and an upside down T, but I don't have any P waves. So the answer to 2 and 3 is no. Then let's measure the width of the funny looking beats, and I can see that they're 0.20. Here is the beat that I've measured. It goes from here to here. This is the end of the QRS. This is the beginning. So when you look at that whole complex together, it's wide. It's 2. It's 0.2. By definition, on our Hughes clues, if you have a beat that is greater than 0.12, this beat originated in the ventricle. This beat, the electrical impulse, came from the ventricle. So I've got 4 beats here, the normal beats that came from the sinus, and then I've got these 4 beats, the funny looking beats, that came from the ventricle. So again, you put all the beats together, it's a rate of 80, but let's look at what are these funny looking beats. Well, the last name of these funny looking beats is ventricles because these beats came from the ventricle. And if you notice the pattern, it's actually pretty regular. Like if you took the space between here to here, you would identify that it's, you know, so long. And if you divided that space in half, about at this point, if I just kind of visually divided it, about at this point is where the normal sinus beat should have occurred. But notice, this beat came early. So the normal beat should have hit here, but instead this funny looking beat came very early or very soon after our normal beat. Now think about a baby. A baby that arrives before its due date is called premature. These beats are ventricular beats. They're ventricular contractions, and they came prematurely. Therefore, these funny looking beats are called PVCs, premature ventricular contractions. How do I know they're ventricular? Because the QRS complex is wide. These are ventricular contractions. How do I know they're premature? Well, you can just look at it visually and see that it came early before the normal beat was supposed to arrive. Therefore, this is sinus rhythm with premature ventricular contractions. Now, anytime you see a ventricular contraction that's wide and bizarre looking, anytime a beat initiates in the ventricle, it will allow the ventricle to contract, but it will not contract on that normal pathway in that normal manner, and therefore your cardiac output is going to be less. So these PVCs will reduce your cardiac output. So is this an emergency? Well, it can be. You have to look at your patient. Let's look at this strip. Let's look at this strip. P waves. I don't see any P waves. There's no electrical activity that's organized. It's just a flat line. Therefore, I can't answer question 2 and 3. I can't measure a QRS. I don't see one. I can't calculate a rate. Probably most of you had said, duh, we know this already. This is asystole. This is flat line, asystole. Let's look at this. Answer the 6 questions. Tell me what you come up with. Or say to yourself, this is... Did you come up with normal sinus rhythm? Well, yeah, that's what this looks like. It's normal sinus rhythm. What if I said to you, here's what your strip looks like, but this patient has no pulse? What does that mean? What does it indicate? What do you think is happening to this person? If you thought this is normal sinus rhythm, you're correct. But as soon as I tell you this patient has no pulse, this means that the heart that's going to beat on and on, the electrical portion of the heart is working just great. That SA node is firing and it's sending the electrical message downstream and it's going to the ventricles and the ventricles are depolarizing. But just like Hitch, the heart must listen to the electrical impulse and respond. In other words, you have the electrical impulse, the cells depolarize, but they must then contract. They must beat. They must pump. Therefore, this rhythm is known as pulseless electrical activity. You have electrical activity. That's all good. But you do not have the mechanical portion of the heart. The heart is not pumping blood. For all intents and purposes, this patient is dead. There is no cardiac output because the ventricles are not pumping. Electrical activity, fine. Pumping power, bad. It's gone. It's not there. So therefore, pulseless electrical activity. Now I showed you normal sinus rhythm, but I want you to know that it could have been any rhythm. I could have put up any rhythm. If there is electrical activity and there is no pulse, the patient is, by all intents and purposes, dead. There is no pulse. You have PEA. It can be anything. It could be atrial tachycardia. It could be atrial fib. It could be atrial flutter. It could be normal sinus rhythm, normal sinus bradycardia. It doesn't matter what the rhythm is. As soon as the words "there is no pulse" is seen, then your patient is in PEA, pulseless electrical activity. Make sense? I hope so. This was a really short one, so hopefully your brain is doing okay. If you have any questions, be sure and contact me, and I can help clarify anything.